Greetings, peeps! First thing I'd like to do is apologize if the audio is a little bit off or different. My clip-on microphone broke, and so I've got to use the microphone directly from the camera, so hopefully it works at least for this lesson, and I plan on re-recording it some other time. But here we go. What we're looking at is a total systems approach to, well, in this case, solving an inclined plane problem. So the total system is something we'd like to look at. Before we broke things down into their individual parts, for example, object 1 and object 2. It's still going to be necessary to do some of that in order to find things like tension, but we can look at the system in total to find something that they share, and that's an acceleration. Both these will have the same acceleration since they're tied together by the same string. They'll be moving at the same acceleration, at least the magnitude anyway. So what we look at is problem number 2 from your inclined problem set. I wanted to bring up something that was somewhat familiar. So what we have here is 2 kilogram mass aluminum on steel and a 6 kilogram mass on an incline. The ramp here, that's copper on steel, and they have different kinetic friction coefficients, which are mu k1, mu k2. And now what we want to do is think about this as a total. This is Newton's second law rewritten in terms of acceleration, the factors that affect the acceleration of the system. So those factors are the sum of all the forces in the system that would affect the acceleration and divided by the total inertia of the system and total. So that's written in pure English here. Sum of all forces affecting total acceleration divided by total inertia of the system. So our goal now, instead of creating the individual free body diagrams and deriving each individual equation to then fuse into this monstrous algebraic exercise, which obviously works but can be slow, especially if you're taking an exam or something like that, you want to maximize your efficiency. So this is going to be more efficient to look at it from a systems perspective. So what we look at here are there no external forces applied. That would mess up the system, right? So there are no external forces, so we just want to reason it out. What's going to happen here? This is the larger mass, and 30 degrees is not that big of an angle, but big enough such that if we were just to let this go, like on the Atwood's machine, it would move, okay? Granted, it's got to exceed static friction, so we're going to make that assumption that it's done that. And so we're at kinetic friction here. And so the total acceleration would be down the ramp. We just look at it, reason it out, look at the values. You can even do a couple of tests to figure out what would happen. But our gut instinct says it's going to be down the ramp, so that we can use that information to then look at the problem in total. So there are no external forces, therefore the total acceleration of the two objects together as a single system will be, yes, down this incline. All right, so we'll be able to develop the problem a little more easily in terms of that relationship here. Sum of all the forces acting to affect the acceleration over the total inertia, which is the sum of the masses. All right, let's try it out in the next frame. Alright, so if you look at the diagram from the prior frame, you'll know that there are certain forces that will affect the acceleration of the system. And the first one is the gravitational force acting at mass 2 down the incline. So it's that component related to the sine of the angle that is going to be responsible for bringing this in a positive direction for acceleration down the ramp. We also know, though, there are a couple things that are going to try to stop that, and that's friction from surface mass 1 in its surface and mass 2 in its surface. Anytime there is a resistive force that's opposite what the system wants to do, which is accelerate down the ramp in this case, that would be considered a negative force. So we have two negative forces and one positive force. The other thing that's going to affect the acceleration of the system as a total is its total inertia, which is easy. It's just the sum of the two masses, m1 plus m2. That comes out in the algebra that we've done anyway, but if we now just know it and reason it out, we have the denominator, and all we really have to worry about is the numerator. So let's go try it out. Here it is in algebraic notation. A total is Fg2 times the sine of theta. That's the gravitational force acting on mass 2. Force of friction 1, that's based on the mass number 1 and its interaction with the surface. F friction 2, friction between mass 2 and its surface, over sum of the forces, sum of the masses, the inertia. Therefore, we have it. That's the expression. Much easier to get when you think about it in a total systems approach than to try to hope that your algebra is good. Well, we still have to do some algebra in terms of substitutions, though. It's important. And that would be here, the force of gravity is equal to mass times gravity. Okay, so Fg2 is m2g. The force of friction for mass 1 on the flat part is mu k times m1g. That comes from mu times force normal, and this part is force normal here. And lastly, we have force of friction 2, which is mu times force normal for that object. That force normal is m2g cosine theta times its mu, and there you have it. I've just taken these guys and substitute them in here. So this is the expression that you'll probably recognize from doing the algebra out for that problem, and here we got it a lot quicker. Okay, so I did the same thing as before, same approach. We plug in the numbers at this point since we have the expression in terms of all the variables that are given. That's the masses, the mu's, and g. And now we're able to solve, and what we get is 0.232 meters per second squared. Okay, how does this help us get tension? Well, the next part would be to try and solve for tension. And to do that, you need to create the free body diagrams as we've always done, and write down one of the equations that has tension. The thing is, this is much easier because we got A much quicker than before. So now that we've got the acceleration, you can use that acceleration, which you'll need to solve for tension. So I'm not going to go through that since we've done that already, but that would be the approach. This is the new stuff here, the systems approach to finding the acceleration, and then you can use that to find any other things, other forces such as tension. So there you go. Hope this was helpful in trying to come up with quicker ways, more logical perhaps, system-wise ways of looking at the same situation. And that's what it is. Here we go. Morad